Hello young people, welcome back. This is the start to Unit 2. We are going to be talking about biodiversity, and this is 2.1 Introduction to Biodiversity. Our learning objectives: explain levels of biodiversity and their importance to ecosystems, understand contributions to losses of genetic diversity, understand how ecosystems respond to disturbances and their relative likelihood to be able to recover, and understand the difference between species richness and species evenness. So let's first sort of break down biodiversity, and we'll kind of look at how biodiversity can be an indicator for how healthy an ecosystem is by talking about how it plays a role in an ecosystem's ability to respond to a disturbance. So we can further classify biodiversity into three categories: genetic diversity, species diversity, and ecosystem diversity. And actually, these are sort of written in opposite order, but really the greater your ecosystem diversity is, and ecosystem diversity is mostly talking about the different variations of places a species can exist within a given area. So for instance, old trees, young trees, moist soil, dry soil, ponds, streams, all within the same ecosystem. That's going to be ecosystem diversity. The higher or greater your ecosystem diversity is, the more species that ecosystem will be able to support. And the more species that ecosystem can support, the more genetic diversity you're going to see within it. So having a high ecosystem diversity will trickle down all the way into a high amount of genetic diversity. I'm going to talk about these in more detail too, but genetic diversity is just a measure of the genetic variation within a species, so we'll dive deeper into that. And then species diversity is the number of different species within an ecosystem. So first, let's look at genetic diversity. So genetic diversity is looking at genetic variation among a specific population of the same species. So the image you're seeing here are the oh so popular labradoodle. Very cute, but if you've ever seen a labradoodle, you'll know they come in all different variations. You'll see the kind of golden color, you're seeing the white and gold color, maybe there's a lighter gold color. That's all genetic diversity. This is expressing a phenotypic genetic variation where you're seeing a change in color, but high amounts of genetic diversity, not only do they give you this, but they also give you a better opportunity to be able to respond to environmental change. So good genetic diversity leads to a higher chance of having more fit individuals as ecosystems change over time. So for instance, if an ecosystem were exposed to some type of disturbance, like a massive forest fire, for instance, you would want a high amount of genetic diversity so that your population, your specific species population, had a chance of still surviving in that area. There's a higher chance that there's a group of individuals within that population that are able to withstand the change to the ecosystem, versus a population that has a much smaller pool of genetic diversity. Now with species diversity, we're talking about the total amount of different species that exist within an ecosystem. So just to give you an idea of how much species diversity we have on the planet, we've identified about 2 million species, which sounds like a lot of species, but it is estimated that we have anywhere from 5 to 10 million total on the planet, which means there's up to 8 million species that we haven't been able to identify. Now that may sound kind of weird, but you have to think about all the different variations in small insects that are challenging for us to find that we may not even be looking for. Additionally, there is extinction happening constantly. So there are species that we may have never even identified that have come and gone in our lifetimes that we'll never even know about. But ecosystems that tend to have more species diversity tend to be much more productive, meaning there's much more energy flow within their ecosystem because there's much more species contributing to that energy flow. They're more resilient. Ecosystems that have more species within them are able to recover from a disturbance to their ecosystem more quickly. And that's going to help restore productivity to an ecosystem after a disturbance. So we want a high amount of species diversity. A A loss or gain of a species from a particular ecosystem generally tends to be a really good indicator that there has been some change or disturbance to that ecosystem. Oftentimes we look at species like frogs as indicators for ecosystem changes because frogs are amphibious, meaning they live both in water and on land. So that because they're exposed to both portions of an ecosystem, the aquatic and terrestrial portion, we tend to see them having the first impacts on whatever that environmental change may be. They tend to be the first species that's impacted by it. So a lot of times if we're looking to see if change has occurred, we'll look at amphibious species. And then of course we have ecosystem diversity. The more ecosystem diversity we have, the more species that we're able to support, the more primary productivity we're able to support. So a higher amount of energy flow, and that of course turns into a higher amount of genetic diversity. Now, really what we're worried about right now, of course, is our current loss of biodiversity as a result of our loss of ecosystem diversity. And this is really what we talked about when we talked about biomes, that because we have this really large anthropogenic impact on our planet right now, we're starting to see a shift in these what we call traditional biomes and traditional climates. So as a result, we're actually decreasing the amount of ecosystem diversity we have on the planet. We no longer have these really distinct biomes with these really distinct temperature characteristics. Everything is sort of melding together into one kind of mid-latitudinal common temperature range. As a result, we're losing ecosystem diversity, we're losing species diversity, and then from there, even more so, losing genetic diversity as those species begin to die out. So those anthropogenic strains, so human impacts on those planets or on our ecosystems, so things like climate change or deforestation or mining, etc., are causing long-lasting problems for all of the different levels of biodiversity we just discussed. So we'll take a little bit deeper of a dive into loss of species. So first we kind of have to understand speciation. So this is when we get a new species added. So we increase the biodiversity of the planet. Speciation, because it happens on an evolutionary time scale, is very, very slow. So on average, we may receive only 1 to 3 new species per year worldwide. Now, speciation really is just something that it means that the species, in order for something to be considered a new species, the species can no longer reproduce with something that is similar to it. So it has gone away genetically so much so that they are no longer the same species. That doesn't mean they look physically or dramatically different, but they can no longer reproduce and have viable offspring. So we see speciation happen over time as we see changes to ecosystems, and individual species within those ecosystems have to adapt to that new area. So speciation tends to be very, very slow, and it doesn't necessarily mean we're seeing this brand new animal that we've never seen before. It may just mean like a lizard, a certain species of lizard is no longer able to breed with another species of lizard. We do have something called background extinction rate. This is the average rate at which species are going extinct. We expect and anticipate that we will lose species each year. That's what this background extinction rate says. That just because our planet is constantly changing and not all species are able to adapt as quickly as they need to, that we will eventually see species go extinct. We anticipate this to be about 1 per every million each year. So if we have 2 to 3 million species on our planet, we should expect to lose 2 to 3 species per year on average. This is not what we're seeing at all. Ours right now is much faster. We're losing about 1,000 species per year. So this is about 500 times the background extinction rate. This is largely due to our loss of ecosystem diversity or anthropogenic causes or disturbances to those ecosystems. So we are very concerned about this current extinction rate. And so much so that we've created these massive lists for the species that are the most in danger of becoming extinct. So things like the snow leopard or this West Indian manatee Both of these are ones that have been on the danger zone red list, getting ready to go extinct list for many, many years, and a lot of it is due to habitat loss for both of them. So I've mentioned a couple times ecosystems and their response to disturbances and how that affects biodiversity, but let's talk about what a disturbance is. So disturbance is any event caused by physical, chemical, or biological agents that result in changes to that ecosystem, whether it be population size or community. Could be something natural like a hurricane, a fire, a volcanic eruption, a tornado, earthquake, etc. Can be anthropogenic, which is what we see more of. Introduction of agriculture, air pollution, deforestation, mining, climate change, all of those are considered disturbances, and they're going to take that ecosystem out of its regular equilibrium. So how ecosystems respond to that disturbance is largely dependent on the types of species and the relative genetic diversity of the ecosystem. So in not every disturbance is a disaster. So depending on, again, the type of species that are present and the relative amounts of species or genetic diversity, it may not be as traumatic as we think. So for instance, if we have a low intensity fire that comes in and kills some plant species but benefits others, then we can still see the same amount of primary productivity or net primary productivity within the ecosystem cycling, because the species that were fire resistant will thrive in that area. So we may not see a change in energy flow, we may see a loss of species, but energy flow may remain the same. In which case this would be a high resistance level, meaning even though this ecosystem underwent a large disturbance to it, it was able to respond in such a way that energy flow and matter within the ecosystem was not disturbed. And that's what the definition of resistance is. Then if energy flow and matter flow are not disturbed within the system is more likely to recover and get back to its original status because energy flow and matter flow are still in existence. Now with resilience, this is how long it will take to recover. So resistance is its ability to continue to cycle matter and energy. Resilience is how much time it takes for it to come back from whatever that disturbance is. This will really largely depend on, one, the specific interactions of species and their interactions with biogeochemical cycles within the ecosystem. So an ecosystem that has a very high resilience can return back to its original state very quickly. Generally, ecosystems that have a high resilience are ones that are the most species and genetically diverse, because you've got individuals within those populations that are able to withstand the disturbance and continue to propagate the population. And then they'll be able to adapt to the changing conditions. Ecosystems that have a lower resilience, that sometimes may never recover from whatever the disturbance is, are generally ecosystems that have a very, very low species diversity and a low genetic diversity. This is why we're so concerned with like taiga ecosystems, because they don't have a really high genetic or species diversity there due to the tough living conditions. There's very few things that can survive. So if biomes like taigas are experiencing dramatic changes in climatic conditions, those species that are really only adapted to live in those areas aren't going to be able to survive. And then what you'll start to see is a movement of the type of species that can live in those warmer climates moving upward, moving towards those taiga biomes or those boreal forests, and really just an elimination of boreal forests in general, and again, more of those mid-latitude biomes. If it is an ecosystem that's so damaged it may never recover, then you may see a total loss of species and genetic diversity from there. A good example of this is soil that's been exposed to drought for a really long time. When soil doesn't have any type of water flow or any type of interaction with the hydrological cycle, it will slowly start to dry out. You've probably seen soil like this before where it gets really hard and cracked, and if you were going to try to like dig into it, you almost can't even like put a shovel in. And then once it gets that point, even if it does rain at some point, the rain will no longer be able to infiltrate or percolate down into that soil. Instead, you'll just see it run off the top. It'll act more like a cement or an asphalt type layer instead of being like this porous, nutrient-rich topsoil layer that we would normally see. And then once water can no longer infiltrate that top layer, then you will no longer see plant growth, because not only will there be no water available, but rooted plants won't be able to root themselves within the hard topsoil layer. So we would say that that's an ecosystem that has incredibly low resilience or no resilience whatsoever. So again, resistance is how affected the energy and matter flow within an ecosystem is. So if something has high resistance, energy flow and matter flow will not be affected. You will still have a similar rate of NPP. If it has low resistance, you'll see a decrease in the amount of net primary productivity. If something has high resilience, that generally means it will recover from a disturbance very quickly versus something that has lower resilience. And that is generally depicted by having, both of these are generally depicted by having a high amount of species and genetic diversity. Now there's something called the intermediate disturbance hypothesis. The intermediate disturbance hypothesis basically states that an intermediate amount of disturbance will lead to the highest amounts of biodiversity. So it's kind of a Goldilocks and the Three Bears situation. Not enough disturbance leads to low species richness or species diversity, and not enough or too much species or too much disturbance leads to too few species as well. So essentially, if we have only rare disturbances, like only every once in a while is our ecosystem experiencing a disturbance, it will only favor the best competitors, which means in an ecosystem, if it rarely has a disturbance in it, only the ones that are most likely to survive, the strongest of the best competitor, they're going to be the only ones that survive. So in this rare case, when a disturbance occurs, you're going to see sort of a mass die out of everything because they're not going to be used to this type of disturbance. If we have a really frequent disturbance, it's going to, again, eliminate all the species except for those that are evolved to live in the conditions that can survive whatever this high-intensity disturbance is. So you're just basically going to get a handful of really, really hardy species that can handle constant disturbance. And then if you have an intermediate disturbance, you get species from both extremes that can persist. So the ones that are fine in the low intensity and the ones that are fine in the high intensity, you get a little bit of both able to survive in a moderate amount of disturbance, which is why you get the highest amount of species diversity in that time. So an example that we see here, or an example that we see in nature, is the amount of algae species that are observed in response to the different amounts of herbivory in marine snails. So these marine snails generally feed on algae. In this case, the marine snail is going to be, the introduction of the marine snail is the disturbance. So if we introduce too few snails, there's a low diversity of algae species because there's no reason for there to be any type of genetic variation. There isn't a lot of predation, so no genetic variation really needs to exist. When we have a high amount of snails present, the only algae that's able to persist is the non-palatable algae to the snail. So all of these snails are going to come in and mass consume all of the algae except for the type of algae that's non-palatable to them. So maybe one type of algae species. Whereas if we introduce an intermediate density of snails, they're going to be able to consume algae from both sides. And we'll get the combination of algae that can survive in both low and high intensity disturbance situations. So in this case, we see the most species diversity. And then, of course, with this hypothesis, because we have the most amount of species present, this will make this this ecosystem more resilient to be able to recover any other type of disturbance because we have a high amount of genetic diversity present. Now, I kind of used this term already, and on the last slide they used it, but they also mentioned the word species richness and species evenness. This is another way that we can measure biodiversity. Species richness is the number of species in a given area, whereas species evenness is the relative proportion of each of those species within a given area. So let me show you an example. So Community 1 and Community 2 all have the same types of species. We've got tree species A, tree species B, C, and D, and both ecosystems have these 4 different types of tree species. We have A, we have B, we have C, and we have D. We have them in both of these sections. Community 1, however, has this, so we would say that both of these have the same relative number of species richness. They have the same amount of different types of species in them. Community 1, however, has more species evenness because we have a more even distribution or relative abundance of each of the species. So we have, in this one, in Community 2, we only see 2 versions of species D. Same thing with species B. We only have 2 versions, and then we have a really high abundance of tree species A. So even though they have the same species richness, we would say that Community 1 is more diverse than Community 2 because we have a higher amount of species evenness. So we want an even distribution of all species. Just because you have 1 or 2 of something doesn't necessarily help, because in Community 2, this implies a very low amount of genetic diversity. And if there is some type of disturbance to this ecosystem, then it's really likely that these species that there's only 1 or 2 of are less likely to respond to the disturbance well, less likely to survive. Okay, I think that's it. Let's talk more in class, and I will see you guys soon. Thanks.